AMD is doing what AMD does best, which is arbitrarily renaming everything to make it as confusing as possible. But they have a new version of FSR today, sort of. Some of the things within it are new, some are not, but they sound new, but they're not new. And what it has done is renamed it to just FSR, but now they're appending an arbitrary word to the end of it as well, which is Redstone this time. So FSR Redstone is officially launching today. That includes a couple of actually new technologies that we're going to be testing briefly today. We didn't have much time with this time. They were really late to getting people access to it before the launch today. So we've done as much as we could fit in that time. But these include some features like plans to add Radiance Caching in the future. That's not ready yet, though. Ray Regeneration, which is available today in at least one game that it seems like everyone online hates, but it's in there. And then FSR Frame Generation's new machine learning model, as opposed to the prior Analytical model for frame generation. Now, AMD also rebranded FSR 4 to just FSR. There's no number now, and that encompasses all of these things today. So that's upscaling as well as the frame generation, everything else within it. We previously published a content piece that looked at the differences between AMD's existing FSR 4 and prior FSR solutions that included upscaling. We looked at frame generation. Today, we're looking at frame generation with the new model. So that's going to be the deep learned one. This simple table from AMD helps to explain everything while also listing GPU architecture compatibility. AMD's prior RDNA generations don't officially support machine learned ray regeneration, radiance caching, frame generation, or upscaling, just the analytical versions of upscaling and frame generation. Parts of this are old information, but you always know your naming system is good when you need a matrix to look it up. But hey, they're improving. Last time they had a naming system they wanted to explain to us, they gave us this. Should we just punch in on that? This is a decoder wheel, all right? That was just a matrix. Big improvement. You've really come a long way, AMD. Thank you. You still got more to go, but yeah, we won't get to it. Look, you went from a circle with like 5 rings of hell to a simple table. That's an improvement. Anyway, today we've got some comparisons for you. So we're gonna do image quality for ray regeneration, where we're looking at just some simple on-off tests. That is unfortunately only in Black Ops 7. That's the only option we have for testing in the multiplayer benchmark is what we're using. We'd like to do a lot more with that, but they're just not ready yet. They don't have it deployed to more places. And then we're also doing some end-to-end total system latency testing, following up on our LSFG latency testing, just because we're set up for it. That'll allow us to look at the impact of frame generation on end-to-end total system latency in just the 2 games where we did the frame generation comparisons today, because that's what we had time for. So we're looking at Cyberpunk and Marvel Rivals today, and that is with the new deep learned frame generation technology. So let's get into all that. Before that, this video is brought to you by the Montech HSO1 and HSO2 cases. The HSO1 and HSO2 cases differ by way of a mesh front or a curved glass front. We previously reviewed these cases in our intensive benchmarking process and found them to be overall high build quality, with thermals comparable between the 2 designs. The rear chamber of the case uniquely brings the power supply forward and perforates the rear wall of the case, allowing for more air movement internally while providing a different look. The rear of the case uses a fan mounting mechanism for 2 separate fans that can be coupled together with a plate, improving convenience. The HSO1 and HSO2 also invert with minimal effort, allowing the computer to present to the opposite side without needing to reconfigure the entire build. Learn more at the links in the description below. All right, so again, we really only had a few days with this, which I'm only emphasizing because I'd love to do a lot more with it, but this is gonna be what we start with because that's the amount of time that they've given everyone to work with it. And we're testing with 2 games initially for image quality. We'd like to do another 2, and then that is to accommodate our ray regen and our latency stuff. AMD's naming scheme is a complete mess. The thing you need to know is Redstone is the word they're using to describe all the stuff we're talking about today. Some of the stuff that's packaged within Redstone is old. It's not new today. So like upscaling itself, not new. But some of the other things we're testing are. And then we're going to use the phrase Redstone to just refer to some of the frame generation deep learn testing that we're doing. All of this is available as of the video going up, so December 10th in the driver package and the games that support it. And then today we're going to get started with some of the image quality, but first the explanation of what all this is. AMD's marketing naming aside, here's the basics. Redstone builds upon what used to be known as FSR 4, while introducing more machine learning powered features. More specifically, AMD released FSR Ray Regeneration and updated its frame generation, both ready for implementation today, as well as FSR Radiance Caching, announced for 2026 sometime. Unfortunately, these latest technologies are only available officially on the RX 9000 series GPUs, at the time of writing this at least, but vast source code leaks for Other AMD technologies have shown that sometimes they can work backwards if someone tries to force it. FSR Ray Regeneration uses a neural network-based denoiser to improve image quality from what AMD calls noisy ray-traced data, with a specific focus on clean reflections, stable lighting, and fewer artifacts. NVIDIA previously debuted its ray reconstruction technology in Cyberpunk, so if you want to see prior examples of this type of technology, we'll link that comparison below for the NVIDIA ray reconstruction testing. AMD Ray Regeneration works by providing the normals depth, diffuse specular information, radiance, and optional light visibility inputs to the neural network, which then denoises the scene. The company said this, quote, "Instead of needing a huge number of rays per pixel, which is very expensive, we can render with fewer noisier rays, and then we use machine learning to reconstruct a clean, high-quality result," end quote. In this side-by-side comparison of Black Ops 7 from AMD using 4K raster, 4K with RT, and 4K with Redstone, we can see the company's intentions. In the highlighted square, we observed noticeable improvements to the surface grain and reflection shimmer. We'll share our own testing in a few minutes to go more in depth with this, but this is what AMD used to set the stage. This feature will be available through in-game implementation by developers. Unfortunately, some of the brilliance and or idiocy here is that AMD is focusing this feature right now with Black Ops 7, specifically multiplayer, which doesn't really seem like the place people are going to use a lot of ray tracing because performance matters in that situation, and also it seems like people really don't like Black Ops 7. But anyway, AMD presented its newer frame generation next, explaining how it inserts new frames between rendered ones to enhance motion smoothness without major artifacts. In the company's F125 demo comparing FSR 3.1 to Redstone, we noticed distinct improvements to the ghosting and artifacts from the car's shadow. AMD described the frame generation pipeline saying this, quote, "First, we have the previous and current rendered frames along with depth and motion vectors. We use the optical flow estimation plus motion vectors to understand how objects are moving frame to frame. Inside the ML network, we predict per pixel motion and appearance, then blend that with motion vector reprojection to generate a new in-between frame," end quote. The newer FSR frame generation is differentiated by the sort of suffixes machine learned versus analytical, but the newer frame gen is available for RX 9000 series GPUs through AMD's December 10th driver, or with in-game implementation from developers. This new version of AMD's frame gen can be enabled via driver-level override in games that already support FSR version 3.1.4 or newer. Something that's totally new for the Redstone launch is FSR Radiance Caching, a method by which to improve the efficiency of ray-traced illumination. Radiance Caching works by pre-training a machine learning model on the behavior of light within a scene. The model is then used during gameplay to infer how RT should look with fewer actual calculations. Radiance Caching in general is not a new concept. AMD published a related white paper in 2022, and NVIDIA published its own in 2021, and has similar features as part of RTX Global Illumination. In an extremely broad sense, it's like ray tracing's own, more advanced version of baked lighting. AMD claims that by using FSR Radiance Caching, radiance can be inferred with as few as 2 ray intersections. FSR Radiance Caching requires direct integration into games and is available to developers now, but isn't in any games yet. AMD expects FSR Radiance Caching to begin appearing in games sometime, they say, in early 2026. Before wrapping up, AMD presented a final Black Ops 7 comparison showing the effects of several Redstone features applied at once. AMD was trying to create a best-case scenario. The company compares 4K, 4K with ray tracing, and Redstone with FSR upscaling, FSR frame generation, and FSR ray regeneration applied. The part AMD didn't address is the inevitable hit to image quality and latency required to fake quadruple FPS. Upscaling isn't new, it's just renamed for branding. Finally, the company announced the release of its FSR Redstone SDK for developers, available on GPU Open, and its UE5 plugin, both accessible starting December 10th. With all that gone through, let's get into some of the actual comparisons. We'll start with image quality. We'll put 2 videos of Cyberpunk 2077 on the screen at once, one with FSR Redstone frame generation, and one with frame gen off, but without labels. This is a blind test. We did a few of these a while ago, and it was fun, so we're bringing it back. Without pausing, try to guess which is which while we talk through the next section here. Feel free to loop the section, but try to resist going frame by frame. Post your comment below before we reveal it. Mostly, we're curious if people can tell. Our test scene shows us driving the Quadro Turbo R VTEC straight through NVIDIA's campus. Corpo Plaza, same thing. At full speed, it's extremely difficult to tell the two apart, with only the most minor differences. 60 FPS YouTube playback doesn't show every frame from our 120 FPS capture, so we'll slow it down. At 50% speed, focusing on sharpness and motion clarity near the edges of the screen will give you the best chance. Try to get the overall feel for each, rather than looking for individual details. Pay attention to the edges of other cars and to the paint on the road. Now, time for the reveal. The right side is FSR Redstone Frame Gen, and the left side is totally stock without Frame Gen. Next, we'll step through the detailed image quality analysis of this scene to cover those downsides. Cyberpunk still has generally impressive visuals 5 years after launch. However, its specific implementations of temporal anti-aliasing and screen space reflections make for a grainy appearance across pretty much everything. The TAA SSR combo also creates ghost trails behind moving objects like cars. It's particularly bad when the trails interact with reflections, and FSR Frame Gen only makes it worse. Comparing Redstone Frame Gen versus FSR 3.1 Frame Gen first on FSR 3.1 before we're even moving forward, on the right side, you'll see a van pass our camera perspective. Dropping 25% speed makes it easy to see the trail of ghosting behind it and a flutter or a flicker at the leading edge. Redstone looks nearly identical. Crossing over the blue glowing advertisement on the road shows Redstone's first clear advantage when looking frame by frame. FSR 3.1's generated frames, which are easy to differentiate due to the doubling of the orange horizontal lines, have an incorrectly placed strip of light at the dividing line between the right tire and the rear bumper. On Redstone's generated frames, the false light doesn't appear at all. However, Redstone still doubles the horizontal lines. Without Frame Gen, the edges of the horizontal bars are grainy at stock. Neither Redstone's nor FSR 3.1's real frames have the same look. FSR upscaling wasn't turned on for any of our runs, suggesting that both versions of AMD's Frame Gen may be altering the real frames before they go out the door. It's also possible that Cyberpunk makes a silent change in the background when FSR Frame Gen is on. Once we're in the sunlight, FSR 3.1 shows another weakness. The rear underside of the car flickers due to the interpolated frames retaining a strong after image. This isn't present at all with Redstone. Hitting the pole is equally rough for both FSR 3.1 and Redstone, as the car's instantaneous change in position results in ugly double images rather than a single intermediate position. That said, it's only a couple frames and is mostly imperceptible at full playing speed. Something that is bad enough to be visible at full speed is severe ghosting that flickers the front and the rear of the car with FSR 3.1's Frame Gen. For YouTube reasons, here it's at 50% speed now. Redstone gets rid of this ghosting almost entirely, showing only a faint flicker, including as the footage continues to slow down. As we emerge outside again and the camera sweeps around, we can see the huge difference in handling between slow-moving objects in the foreground and fast-moving objects in the background. The distant buildings on the left turn into a mess on every other frame with FSR 3.1 and Redstone. When there's no Frame Gen, it's not an issue at all, and every frame is clear. Redstone Frame Gen looks smoother in motion compared to the stock 60 FPS test, but it does lose some image clarity in places. That's the core trade-off of visual smoothness with Frame Gen. There's also latency, but we'll get to that soon. Rapidly flipping the camera to reverse is far too much to ask of either of the FSR Frame Gen solutions, but the absolute visual mess is contained to single frames. The rest of this scene is mostly more of the same. In Cyberpunk, Redstone Frame Gen shows fewer significant or visible issues than FSR 3.1 Frame Gen. So, in that way, Redstone is an improvement, but it still suffers from a lot of the image doubling in the objective sense. Next is image quality analysis in Marvel Rivals. Like in Cyberpunk, FPS is capped to 60 in-game, and the capture is at 120 FPS. The difference between the Frame Gen solutions is more subdued than in Cyberpunk, so we'll focus more heavily on frame-by-frame analysis rather than full motion. As a general note, Marvel Rivals applies significant sharpening by default, so the visual crunch factor you'll see throughout is native to the game. FSR Redstone and FSR 3.1 at full speed appear virtually identical at the character select screen and when running forward out of spawn to show off our sick aiming skills. At reduced speed, Rocket's legs appear to have slightly less visual jitter with Redstone than with FSR 3.1. The animation while throwing his E ability also looks smoother than FSR 3.1 when viewed at significantly reduced speeds. As we turn to face the enemy bots and strafe left, both FrameGen solutions show strong visual stability in Rocket's character model. There's some sporadic fringing and distortion in the spaces immediately surrounding faster-moving foreground elements, but it's hard to say which version of FrameGen handles it better. It's a little more variable, so you can decide for this one. The first significant issue appears when the friendly bots resurrect. Freezing on this frame from FSR 3.1 shows doubling of the bot's nameplate and the yellow cubes. There's also a faint after-image void in the glow effect along the right edge of Rocket's model and light warping on the right edge of the friendly bot. Redstone's capture shows more severe distortion of the bot's name, but the after-image left in the glow effect is significantly reduced to the point that it's barely there. When strafing back to the right, projectiles and visual effects from shooting flicker halfway out of existence on the generated frames of both Redstone and FSR 3.1, which is slightly visible in motion. We'll drop to frame-by-frame comparisons. During this hard right mouse turn, Redstone has its first solid win for the scene. As Rocket raises his gun, Redstone keeps the area between his head and his gun looking correct throughout. But FSR 3.1 completely falls apart into a heavy blur across multiple generated frames. Dashing off of the balcony looks generally clean for both. After landing, Rocket's shadow jitters with FSR 3.1 while running, but Redstone earns the point for keeping the shadow completely stable. You can also see this after picking up the ult charge and turning. Going frame by frame as Rocket lifts his gun to fire, we see a no-win situation between the two FrameGen solutions. FSR 3.1 has heavy ghosting at the front and right edges of the gun. Redstone shows bad doubling in front and distortion across the surface of the gun. Neither is good, but Redstone is possibly worse here. At 25% speed, the orange rings that jitter as they rise up around Rocket with FSR 3.1 jitter less with Redstone, and have zero jitter when FrameGen is off, so as you'd expect, at least if you can run FrameGen off, it generally should still look cleaner. Going frame by frame as Rocket leaps to start a wall run, we see both FrameGen models struggling with the sudden movement, appearing as various blurs and distortions. When brought up to 50% speed, Redstone's motion reads as noticeably smoother than FSR 3.1's motion. When the top railing comes into view and starts to pass in front of the rooftop boxes, pay attention to how FSR 3.1 tends to incorrectly drag chunks of pixels from the background elements along with the railing. Redstone technically does a better job of retaining spatial continuity, but instead suffers increased blur, like it's blending the foreground and the background pixels together. We threw in a quick mouse shake test at the end of the run. This is less controlled as a testing process, but it's designed to root out real-world worst-case scenario results. Redstone FrameGen had more distortion, while FSR 3.1 FrameGen had more blur. Taken as a whole, Marvel Rivals was closer to a toss-up between AMD's previous and next-gen FrameGen interpolation models compared to in Cyberpunk. It was difficult to find many visual errors that were obvious in motion, but we'll call it in favor of Redstone for the multiple instances of reduced jitter in shadows and effects. We'll get into latency testing now, following our recent Lossless Scaling Frame Generation latency benchmarks. Testing includes benchmarks with the Tech Team GB latency tester used during Cyberpunk 2077 and Marvel Rivals, both with and without FPS caps. If you want to know more about the testing methodology for this section, you can check our Lossless Scaling latency video that we'll link below. We're not going to go over it again here, it's in that one. Marvel Rivals is first in this game, enabling frame generation forces XELL, or Intel's latency reducing technology, to on, and it also forces an uncapped FPS. XELL remains off when frame generation is off, so baseline is still without any latency reducing technology. Without any frame generation and without anti-lag, just playing the game normally, we end up with a 15.7 millisecond total average latency end to end and an 18.2 millisecond 5% high latency. Obviously, all of this is contingent on things like frame rate, which impacts latency, and also the screen refresh and things like that. Enabling anti-lag and keeping frame generation off pushed it to 14.9 milliseconds and 17.5 milliseconds. That makes the average total end-to-end latency about 5.1% reduced from the stock performance of 15.7. Given the generally more sensitive latency testing parameters, this isn't that far outside of what we think is a reasonable error for this, so it might not really be doing anything. Enabling Redstone frame generation puts us at 20.1 milliseconds total and 23.4 milliseconds for 5% high. That means the stock result of 15.7 is reduced from the Redstone results by 22%, so enabling frame generation at all definitely had an immediate impact on latency. Enabling anti-lag didn't really seem to do anything. keeping us at 20.5 milliseconds with Redstone FG and 23.8 for the highs. The FSR 3.1 results were also about the same as the Redstone results at 20.3 and 20.2 milliseconds total end-to-end average latency. Frame generation has an impact on the latency overall here, and we're going to skip our FPS cap results since our only option to really do it that way was to force that externally with rivals, which could introduce unrealistic scenarios since it's via external software like AMD's Radeon suite. Cyberpunk 2077 without an FPS cap is next. In this benchmark, the total end-to-end system latency was 34 milliseconds without any frame gen, with the settings we used at the frame rate we had, basically tested when you're playing it normally. Enabling anti-lag and keeping frame generation off didn't do anything, keeping both the average and the 5% high latency results within error of the original results. Enabling frame generation increased the latency by around 4 to 8 milliseconds, depending on if you're looking at average or highs. Frame generation with Redstone and with FSR 3.1 were within reasonable error during testing, making them about the same at 39 to 40 milliseconds end-to-end in testing. Anti-lag was also within error of the non-anti-lag tests. We asked AMD about the anti-lag results in Cyberpunk because it seemed like the driver toggle wasn't doing anything. AMD told us that anti-lag 2 is on by default with Cyberpunk, or at least is with the test configuration for Redstone that we're using, and so toggling it elsewhere, they say, won't change anything. With that in mind, if AMD is right about it being on by default here, then that makes sense for the results. Now tested with an FPS cap of 60, Cyberpunk runs a 40.5 millisecond end-to-end latency with frame gen off, or 48.7 milliseconds for the 5% high latency results. FSR Redstone frame generation puts us at 45.7 milliseconds for the average, and a significantly higher 60.4 milliseconds for the 5% highs. This is a big excursion from the spacing between them that we saw with frame generation off. Frame generation noticeably worsens Cyberpunk's latency and also reduces the consistency of the latency test to test, which makes the experience less predictable. That's arguably just as important as the latency, because predictability is tied to all of this. Both of these impact sort of how the game feels as a player. FSR 3.1 and Redstone didn't have meaningful differences in average latency or the 5% highs. They're about the same in this regard. Getting into the ray regeneration testing, we're testing with Call of Duty Black Ops 7 and its multiplayer benchmark. The first comparison is with Ultra Graphics, FSR off, RT high, and toggling ray regeneration functionality for A/B comparison. Since this is a ray tracing technology, we're going to focus on comparisons on scenes where we expect to see more of an RT impact, such as with water or reflective surfaces. We'll toggle between regen on and off for captures of the first scene. With regen on, the back of the hand has more light bouncing or reflecting off of it. The pistol also has more edge lighting, and the pool, which is the obvious choice, just generally looks less muddy and higher resolution as an image, as opposed to with regen off, where it looks fuzzier. The pool at the back corner in particular looks like a weirdly low resolution render, even though render resolution and FSR settings are identical between these two comparisons. We'll let the clips play side by side for a moment in real time so you can get a general feel for the differences between regen on and off. Underwater, we didn't observe many differences between the two settings. You can occasionally see some lighting differences, but those could also be caused by dynamic element changes within the scene or slightly out of sync frames. Entering a room with a reflective tile floor gives us an easy opportunity to look at the RT impact from ray regeneration. Doing another few frame by frames and freeze frames here, we notice that the reflections on the floor, similar to the pool earlier, just generally have better image clarity and sharpened borders. Ray regeneration disabled has more visible grain or noise in some of the borders of these reflections, particularly at the edges of some of the harder lines in them. Walking a few steps forward, but before we get any kind of fire or dynamic lighting changes, there are also a few changes at the back of the room, such as at the top of the fridge and along the lower diagonal panels of the ductwork. We'll let the missile impact play out for a second and side by side. However, due to the dynamism and slightly out of sync pacing of these events, it's difficult to do a perfect A/B lighting comparison. We noticed that there's some elements that are not the same every single time, so it's not a good candidate for comparison. Back on the balcony with another freeze frame, we noticed the small pools of water on top of the raised wooden platform were brighter and had more edge lighting with ray regeneration on. The same was true for the back left pools of water on the concrete tiles. Before the missile hits the ocean, one look at the horizon also shows darker shading along the water and landmass for the capture with ray regeneration enabled. We also captured the same scene with ray tracing set to low rather than high, with all else the same as previously. In some quick jumping around to the same types of scenes we just compared, the differences match with lower quality just generally because RT quality is lower. In our quick test today, changing the ray tracing quality didn't change where or when the differences in ray regeneration were visible, just sort of the overall quality of the ray tracing. In the past, NVIDIA's ray reconstruction had some bugs and issues in Cyberpunk 2077. We'll play that while we're talking now. Unfortunately, AMD's ray regeneration doesn't work in this game currently, so although we'd really like to do it, we can't test those same scenes or the same bugs. In theory, it's possible that both of these technologies have some shared shortcomings. Using our previous NVIDIA test as an example, those have historically been things like the ghosting of the point light you're seeing, such as on this satellite dish. Strafing side to side with bright lights also had some negative effects with the NVIDIA option, or just roof textures with shading popping in and out. The single option of testing ray regeneration in a game no one wants to play, using a mode no one wants ray tracing for, really limits our ability to do some more serious comparisons right now. As ray regeneration develops, if it gets deployed in more games, we may revisit it in the future. All right, so that's going to be it for this one. We have a lot of pieces now on image quality comparisons for upscaling technologies, but also the frame by fake frame comparisons, which are pretty fun to do. So if you want to check those out, we'll link some of those below. Most recently, these included Lossless Scaling Frame Generation image quality comparisons. That is the $7 tool on Steam. We have also AMD previous FSR and AFMF and in-game frame gen comparisons from earlier this year with the 90 series launch. So we've got all those if you want even more of this. And then if there's specific interests here, we can expand on this and do some more of it. But that's at least your quick flyover for the new Redstone launch to get everyone kind of situated with some of the terminology, and then we'll come back to it for more. So thanks for watching. Subscribe for more. Go to store.gamersnexus.net to support us directly, or patreon.com/gamersnexus, and we'll see you all next time.